In the shadow of retreating giants, a new world is stirring. As Earth's glaciers recede at a pace we've never seen before, they are unveiling vast, barren landscapes, a blank canvas upon which nature is beginning to paint new ecosystems. This is one of the most rapid and widespread environmental transformations of our time. From the high peaks of the Himalayas to the fjords of Alaska, these nascent worlds offer a unique, real-time window into a fundamental ecological process, the birth of life from sterile ground. Today, we journey into this thawing frontier to witness how an ecosystem is built from scratch and explore the unexpected perils that come with this creation. Let's start with the sheer scale of this transformation. Glaciers cover about 10% of the Earth's land surface, and they are shrinking fast. The biggest melts are happening in Alaska, the Canadian Arctic, and around the edges of Greenland and Antarctica. But the fastest rate of loss is in places like the European Alps and the South American Andes. As these immense rivers of ice vanish, they expose land that has been buried for centuries, even millennia. The area of new land is staggering. Projections suggest that by the year 2100, we could see new terrestrial, marine, and freshwater ecosystems emerge over an area ranging from the size of Nepal to the size of Finland. That's up to half of the world's current glacier area outside of the major ice sheets, gone, replaced by a geological newborn. This newly exposed terrain, called a glacier foreland, is a chaotic jumble of rock, gravel, and fine sediment. It's a stark, sterile environment, seemingly devoid of life. This is the starting point for a remarkable journey of ecological transformation known as primary succession. Unlike secondary succession, which happens after a disturbance like a wildfire in an area that already has soil, primary succession is the process of life starting from absolute zero. These glacier forelands are, in essence, natural laboratories for studying how life takes hold and ecosystems develop from the ground up. So where does life begin in such a desolate place? The very first organisms to colonize these barren landscapes are invisible to the naked eye. Long before the first moss or blade of grass appears, a complex and dynamic community of microorganisms takes hold. These are the unsung heroes of primary succession. And they don't travel far. The initial colonizers largely come from the glacier itself. As glaciers move, they scrape and grind the underlying rock, and the ice, meltwater, and sediment within them harbor a surprising diversity of microbial life. When the glacier retreats, these microbes are deposited onto the new land, becoming its first inhabitants. Among the most important of these pioneers are cyanobacteria. You might know them as blue-green algae. They are remarkable because they can produce their own food through photosynthesis, just like plants. But their most critical role is nitrogen fixation. Nitrogen is an essential nutrient for all life, but it's incredibly scarce in new glacial sediment. Cyanobacteria have the unique ability to pull nitrogen gas from the atmosphere and convert it into a usable form, like ammonia. This process is a crucial first step in enriching the sterile ground, making it more hospitable. Studies in the high Andes show that in the first 5 years after a glacier retreats, the diversity of cyanobacteria skyrockets, corresponding with a dramatic increase in soil nitrogen. These microbes also act as ecosystem engineers. They produce sticky, organic substances that bind soil particles together, creating a thin, living layer on the surface, called a biological soil crust. This crust stabilizes the ground, reduces erosion, and helps to retain moisture and nutrients, literally building the foundation for all the life that will follow. Following this invisible microbial takeover, the first visible signs of life begin to appear. Lichens and mosses are the next wave of pioneers. Lichens, which are a fascinating symbiotic partnership between a fungus and an alga or cyanobacterium, are perfectly suited to the harsh conditions. They can grow on bare rock, and the acids they produce help to break down the rock surface, a process called biological weathering. This creates tiny cracks and crevices where dust and organic debris accumulate, forming the very first pockets of soil. Mosses soon follow, anchoring themselves in this thin new soil and adding more organic matter as they grow and decompose. This gradual buildup of organic material is critical. It improves the soil's structure, its ability to hold water, and its nutrient content. The warmer the climate, the faster this soil-building process occurs. As these pioneer communities of lichens and mosses become established, they pave the way for the first vascular plants. In many alpine regions, these are small, hardy perennials with specific adaptations. They are often low-growing, forming cushions or mats to protect themselves from high winds. Many have hairy leaves to reduce water loss and protect against intense UV radiation at high altitudes. The specific species vary by region. In the European Alps, you might find alpine rock cress and various saxifrages. In southern Norway, it could be alpine meadowgrass. But one of the most significant events is the arrival of nitrogen-fixing plants. The classic example comes from Glacier Bay, Alaska, where a shrub called Sitka alder plays a monumental role. Like the cyanobacteria, alder has a symbiotic relationship with bacteria in its root nodules that can fix atmospheric nitrogen. The presence of alder can dramatically increase the amount of nitrogen in the soil, accelerating its development by centuries. This enrichment paves the way for later, larger species, like the towering Sitka spruce. The process isn't always a simple straight line, though. While alder enriches the soil, dense alder thickets can also shade out and inhibit spruce seedlings, creating a more complex dance of facilitation and competition. As the plant community develops, creating food and shelter, the animals arrive. The first ones are typically small invertebrates. Springtails, sometimes called